So we have studied the rotational property of a vector, and vector can be rotated by multiplying the rotation matrix, and we have obtained the formula for describe the rotation matrix in terms of exponentiated one, in which exponential of minus I angle multiplied by a matrix. Here the matrix is called the generator, whose property is the traceless and Hermitian. Because the generator is traceless Hermitian, the rotation matrix has the determinant 1 plus 1. So as a continuous group, the rotation matrices form a group of orthogonal group, and with the determinant plus 1, that is SO3. Extending that idea to further study the transformation properties of quantum mechanics in this class, and beginning with the rotational property of a three-dimensional vector, we study the rotational property and translational property and the time evolution property of the quantum mechanical wave function based on the idea of classical mechanics developed with the Poisson bracket. We will study the correspondence principle between the Poisson bracket in classical mechanics and the commutator relationship in quantum mechanics. Based on this idea, we will extend to find the form of the time-dependent Schrödinger equation based only on the correspondence principle. Okay, let us first study the fundamental properties of the angular momentum. The orbital angular momentum is expressed as a cross product L equals x cross p. And the component, ith component of the orbital angular momentum was epsilon ijk, xj, pk, where j and pk are summed over. If we compute the Poisson bracket of coordinate and its conjugate momentum in the Cartesian coordinate system, the Poisson bracket is xp, xp, and xp, px, where k is summed over. The second piece vanishes completely because coordinate momentum coordinate crossed partial derivatives. The surviving term, non-vanishing term, is this one, delta ik, delta jk. The correspondence principle between the classical mechanics and quantum mechanics is that the Poisson bracket is replaced with IH bar, divide the quantum mechanical commutator divided by IH bar. Let's see. We already know the quantum mechanical operator for momentum, that is h bar over I, and jth component is the partial derivative with respect to coordinate xj. If we compute the commutator, we find IH bar delta ij. The tensor structure of this Poisson bracket is exactly the same, except the normalization IH bar appears additionally in the quantum mechanical commutator. The correspondence principle is that Poisson bracket is replaced with the quantum mechanical commutator, except that the normalization factor IH bar should be multiplied. In this class, by making use, we will extend this idea to derive various properties of quantum mechanics. Let us first prove this is the fundamental commutation relation for quantum mechanics that is related to the coordinate and the canonical momentum. The rotational property of basic properties of the rotation matrix states that the Poisson bracket of orbital angular momentum, Li and Lj, is actually the epsilon ij k Lk. That means L1, L2 gives L3, L2, L1 gives minus L3, L2, L3 gives L1, L3, L2 gives minus L1, L3, L1 gives L2, L1, L3 gives minus L2, something like that. This one, once we prove this, by making use of the correspondence principle, we just multiply IH bar to the right hand side and replace the Poisson bracket with the quantum mechanical commutator. The basic reason for having our IH bar factor appears like that. In quantum mechanics, the wave function of a state, free particle state, for example, is expressed as the exponential I kx minus omega t. And the Broy's wavelength hypothesis gives a momentum of a quantum mechanical particle can be expressed as a product of k and h bar, where k, the wave number k, is a 2 pi over lambda, and h bar is the Planck constant divided by 2 pi. And the energy of a particle is assumed to be the same as the energy of a photon that was obtained by the photoelectric effect. So energy becomes h nu, and we multiply and divide by 2 pi to find h bar and omega angular frequency. Using this, the wave function of a free particle can be expressed as a exponential I over h bar px minus et form. If we want to find out the momentum from this eigenfunction, to read off the momentum, we multiply h bar over I and take the derivative of with respect to the coordinate. To find the energy, what we do is IH bar multiplied by the time derivative. Then that is the eigenvalue problem and the eigenfunction for the free particle, and those are the eigenvalue for momentum and the energy. Alright, so let us continue to study the Poisson bracket of the orbital angular momentum piece by piece. Li Lj is the Poisson bracket for the Li and Lj can be expressed in this way. Lij, XL, PL, PL, XL. Okay, this is the classical mechanical Poisson bracket. We substitute this one. For example, L1 equals epsilon 1 AB XA PB style. So, first component of the orbital angular momentum can be computed x2 p3 minus x3 p2. Applying this, the first factor in the first term can be computed Li epsilon ijk and derivative XL, classical definition of the Li is epsilon ijk xj pk. The derivative acts on the coordinate only, so this one gives a Kronecker delta JL. Right? Okay. And if I consider LJ and PL, this one, we have this one. Just to replace I with J. So I with J. But this one is a derivative with respect to
먼저 잠금 해제가 필요해요.
this one xj, this jab, xapb, that's fine. And then take the derivative with respect to pl. So this one gives a Kronecker delta for b and l. Okay. Okay, so now P has been removed, replaced with the delta LB, and B is replaced with L to find the epsilon J A L X A. Product of this is this product, epsilon LKI PK, epsilon L, push this L forward twice, then we do not have change in sign, LJA, XA. Repeated index is L, so this should be expressed as Kronecker deltas K. So LKI, LJA, KJIA, and minus KAIJ, multiplied by this factor gives KJ, this is XJ, PJ, IA, XA becomes XI, KA, P dot X, delta IJ. The next term, they are the same except that I and J are replaced. So if I replace I and J, exchange I and J, they are symmetric. So if I subtract this one minus this, we find this one cancels. The result is XIPJ subtracted by XJPI. And actually that is the orbital angular momentum component of K with the overall factor epsilon ijk. Therefore, LILJ's Poisson bracket is epsilon ijk lk. And applying the corresponding principle, quantum mechanical commutative for Li and Lj is IH bar epsilon ijk lk. All right. We can also consider the fundamental commutation relation. Poisson bracket for coordinate and momentum is delta ij, and applying the correspondence principle, commutator xi and pj, should be delta ij multiplied by the overall vector I normalization vector IH bar. We notice that the momentum operator in the configuration space is H bar over I derivative with respect to corresponding coordinate. It can be extended to the three-dimensional case that we find that the momentum operator is H bar over I del operator. In Cartesian coordinate, this one is H bar over I coordinates. And in the cylindrical coordinate, derivatives are IH bar over I scale factor multiplied by this. So cylindrical coordinate, spherical coordinate, we can replace the momentum operator in this way. Poisson bracket can be continued to study. We recall the Hamilton's equation. It is necessary to describe the Poisson bracket in an easy way. For any mechanical variable A and B, Poisson bracket is expressed as the QP and PQ derivative subtraction. If we substitute QI and PJ instead of A and B, we may obtain the fundamental commutation relation in any generalized coordinates. If we substitute them, QIPJ, QIPJ, QP, PQ. The only surviving term is this one, delta IK, delta JK. Therefore, the Poisson bracket in any generalized coordinates for the coordinate and the canonical conjugate momentum is delta ij. So by applying the correspondence principle of the quantum mechanics and classical mechanics, what we obtain for any generalized coordinates is coordinate generalized momentum, the canonical momentum equals IH bar delta ij. Therefore, in the configuration space, the scale factor is removed. The Pi is defined by this one. So the scale factor does not appear in the expression. So we return to the angular momentum. This was the Poisson bracket in classical mechanics, and this is the commutation relation for the angular momentum in quantum mechanics. This is the classical mechanical definition. This is the quantum mechanical definition in the configuration space, in which x is a number and momentum becomes a derivative operator. In the spherical coordinates, we can express position to be radius multiplied by unit vector along the radial direction. Gradient is expressed as r, theta, and phi contribution with the coordinates, and the additional factor is the scaling factor, scale factor, to make this denominator have the dimension of length. X cross del operator is then calculable. R is multiplied in here. The cross product R cross R is 0. R cross theta unit vector should be phi. R cross phi becomes a minus theta. Factors of scale factor R cancels, and this here we have angle, polar angle derivative, and we have azimuthal angle derivative with additional vector. Because r hat, theta hat, and phi hat are given in terms of the Cartesian unit vectors like this, we can pull out the Cartesian components of this orbital angular momentum expressed in terms of the polar coordinates. So L1 is E1 dot L. So we pull out the theta hat and phi hat's E1 dependence in here. We can read off and substitute in here to find the expression for the x1 and expression for the x2 and expression for the x3. We noticed that the contribution for E3, L3 is the derivative of azimuthal angle. So orbital angular momentum Lz is the conjugate momentum of the coordinate phi, that is azimuthal angle, with respect to the rotation about the z-axis. Let us consider a linear momentum as the translational generator. As we know, the angular momentum is the generator for the rotation. Actually, the linear momentum is the generator for the translational operation. In the configuration space, we studied that the momentum is a derivative operator with the over scaling factor h bar over I in quantum mechanics. The fundamental commutation relation for any generalized coordinates q and its conjugate canonical momentum should be IH bar delta IJ because of the correspondence principle. The Poisson bracket of a coordinate and its conjugate canonical momentum was delta IJ in the classical mechanics. Suppose that we have a quantum mechanical wave function of psi of x. If we translate this wave function by a plus a, then what we really have to do is replace the argument of this function with its inverse transformation. That means x minus a. What we want to do is to translate by a, but the argument of this function should be replaced with an opposite way, translation by minus a. And when we studied the vector calculus in the first part of this lecture, the shift of a function by this amount can be expressed as the Taylor series expansion. And that exponentiated form does have the del operator, and this del operator can be safely replaced with quantum mechanical operator, momentum p up to over a vector I over h bar. Therefore, the translation, in order to translate a wave function, what we just have to do is multiply this translational operator, that is exponential minus a dot gradient. And when we replace this derivative operator with the momentum operator in quantum mechanics, it becomes a minus I real number multiplied by this Hermitian operator. Therefore, the translation can be made by an exponential function as an operator, and momentum is indeed the generator of a translational operation. Okay, if you translate a particle at point x by plus alpha, then what we really need to do is the position addition. If you rotate a column vector about the z-axis, then xy components will change like this. However, if you want to do that in the wave function or state get, what we really have to do is replace our argument by those inverse transformations. So translation by plus a means replace argument by x minus alpha, plus alpha becomes minus alpha, rotate by angle theta, then replace the argument with the vector with opposite direction rotated value. In summary, if I translate some vector, it becomes a plus, but inverse transformation minus, and this argument is replaced with this inverse transformation. Rotate the vector, then we have this kind of form, and new coordinates will be like that. However, argument of a function should be replaced with the inverse transformed one. Okay, let us consider a wave function and a state in a Hilbert space. As you notice, the psi, the wave function of a quantum mechanical system, is actually represent a quantum mechanical state, and normalization of the wave function is given by the integral of the absolute value of the function square is 1. This is a continuum extension of the finite case in which you have finite n independent eigenstates of an operator, and that eigenstates are expressed in terms expressed as the eigenkets, and eigenkets are normalized. Then those unit normalization eigenkets are a construct, a basis set for the Hilbert space. So in the finite case, we have this kind of representation to list up the vector of n components, and to have a scalar product of the two states with like that. However, if you have infinite number of quantum states, then the continuum limit, the summation that appears in the evaluation scalar product is transformed, can be rewritten in the form of integral. A simple example is that the scalar product of two Euclidean vectors. Two Euclidean vectors can be expressed in terms of sum of the product of ith Cartesian components. The ith Cartesian components can be read off, each ith Cartesian component can be read off by multiplying by taking the scalar product with the basis vector with each vector. If you flip the order, this is actually the transpose of a matrix representation of this vector, and the column vector as a matrix representation for the unit basis vector for the Euclidean space. In opposite way, you have a y put here, and transpose of the unit matrix, unit Euclidean matrix. And we find that this is a kind of direct product, and this direct product summed over the indices I for the Euclidean space, you will find this one should be identity. This identity matrix shows that this can be expressed as a transpose of vector x and column vector y. This calculation should be the same as the scalar product between x and y. Here we notice that the summation of the direct product of a unit basis vectors over the all possible space all the dimensions, we have the identity. That is the simplest example of the completeness relation. We'd like to extend this idea to various examples that appears in the Hilbert space that we are interested in. Let us compute the scalar product of the two eigenfunctions of a quantum mechanical system, which are orthogonal. We have psi I. In the finite case, this is phi I dagger phi j, something like that. And in the continuum limit, this one can be validated as an integral of the wave function psi I star and psi j integrated over the space. And by definition, this is a scalar product between psi I and psi j. Let us substitute the identity operator. Before we do that, this one is x psi j. By definition, we define the wave function that is the projection of a state ket onto the x space. We define, and the psi star x is its a complex conjugate. Its complex conjugate is just a flipped order. This is complex conjugate. This is a number. So we have this vector that is psi star x, all right, and integrated over x. That means we have psi star x is psi. Okay, psi integral psi I x because this one is this scalar product. That means we have another completeness relation. Integral over x of the direct product of state ket composed of coordinate, it is just identity, right? In a similar manner, we can compute the value of A sandwiched by the two states I and j. This can be understood as the scalar product between psi I and A psi j. And this one can also be written in the form the operator A appears in the middle and psi I psi j on the left and right. Right. Next, we can move this one. By definition, this A can be expressed as in terms of A dagger size dagger. Therefore, in that case, the operator can be included in the left-hand side with the dagger sign, Hermitian dagger, psi I. The overlap with the Hermitian dagger psi I with the psi j will be that one. Anyway, in summary, we have a state ket or state vector. This is bra ket. This is ket and this is bra. Bra state or bra vector. Ket state or ket vector. This overlap with the position and the ket vector is defined by the wave function. And if left and right are flipped, then we say this is complex conjugate of that wave function. So we have also found another completeness relation, the integration over the direct product of the coordinates is just identity. Completeness relation can be summarized in such a way. Any states that are orthogonal and that spans a Hilbert space can be constructed as a direct product and summed over all possible states, then it becomes one. That means this expansion will give exact reproduction of the original function in any case. Simplest example for the Euclidean vector expansion in terms of unit basis vector can be made as a direct product of the unit vectors summed over all given dimensions is identity matrix. In a matrix form, once you find out the n orthonormal eigenvectors of Hermitian matrix, then that constructs the unit basis vectors, and using that unit basis vectors you can construct a direct product and summed over all possible states to find that is equal to the identity matrix. This one stems from EI, EJ, scalar product is delta IJ. This is a representation of EI, EJ, something like that. This matrix form and this bracket notation, this is delta IJ. Here, quantum mechanical states with I and J, they are orthonormal, delta IJ. Only if we have a unit normalization where our completeness relation is reproduced. So, thus the quantum mechanical state should be normalized to be the canonical delta unit normalization. Then our completeness relation is always valid. And all right. Completeness relation is related to the multiplication of identity matrix or identity operation, and identity operation is carried out twice, then that does not make any difference at all. So identity operation twice, you will get another identity operation. So suppose that we have identity, then we multiply this operator twice. Because this is dummy variable, we use the different dummy variables. Here we find the scalar product between two unit states that gives a canonical delta, delta Mn. This the direct product has the different indices. However, this delta Mn gives the same index for the two pieces. Another identity operator was integral over the space with the directed product of the coordinate cat and bra. And when you square it, you will find this scalar product with the two coordinates x and y. But you will find that it should be the same as identity operator. In order to be the same as this identity operator, this scalar product with the two coordinates x and y as variables, they must be the same as the Dirac delta function. This is the reproduction of that calculation. All right. Completeness relation can also be written in the following way. We have 2A functions with the same index but with different coordinates, and one has the complex conjugate, the other has not. Therefore, summed over n, this one is a psi n x and this one is a y psi n. Because this is a number, numbers can commute, so replace the order, but we find there is a summation over n. So we combine these two as a direct product and sum over n. What I find is identity operator. That means this is the projection of two coordinates x and y. But we just have found that this is the Dirac delta function. Because it is a Dirac delta function, this is Dirac delta function. This is, what's that? By making use of these operators, these wave functions, we can construct the Dirac delta function out of this. Okay? Okay, so this one can be also extended to the further. We consider a state ket psi. State psi, if we multiply the identity operator, that can be expressed as a direct product of eigenkets summed over all eigenstates. Then the function f of x, the function psi of x, can be projected out by sandwiching the position bra, the projectile of the position bra. Then this identity operator is placed in this, and this is, what's that? Projection onto psi n of the wave function. We insert identity operator in here. Identity operator is an integration over y for direct product of position ket and bra. Alright, this one is a function of y, and this is because this is identity, we have x and y, and this is a Dirac delta function. So Dirac delta function multiply the function of y, then we end up with the psi of x. Alright, and the Dirac delta function is the overlap of the eigenkets for the position x and coordinate y. And again, we insert the identity operator in here. By summing the direct product of the eigenkets, we find that the product of eigenkets for a given eigenstate with a different coordinate, and one with the normal and the other with the complex conjugate, summed over all possible states, will always give the Dirac delta function. This one can always be applied to any special functions that satisfies the boundary conditions and construct a complete set for describing arbitrary solution for that boundary value problem in terms of those spatial functions as a basis vectors. Let us continue to study the correspondence principle. This is the last stage of this chapter to find out the equation of motion for the quantum mechanics that is called the Schrödinger equation, time-dependent Schrödinger equation. Okay. So correspondence principle states that the commutator, this Poisson bracket of an arbitrary two mechanical variable is expressed as the quantum mechanical commutator divided by the scale factor IH bar. Let us consider the total time derivative of a mechanical variable in classical mechanics. It is the total time derivative of the mechanical variable. And mechanical variable is a function of a coordinate and its conjugate momentum, chain rule can be applied to compute the partial derivative with respect to the coordinate and time derivative of coordinate plus partial derivative with respect to the momentum, conjugate momentum, and its time derivative, and partial time derivative of that operator, of that mechanical variable. We apply the Hamilton's equations to rewrite this. Then Q dot is replaced with the derivative with respect to the conjugate momentum, and P dot is replaced with minus of the derivative, partial derivative of the Hamiltonian with respect to the coordinate. If we substitute in here, this expression becomes a Poisson bracket of the mechanical variable A and the Hamiltonian plus partial time derivative of operator. If we consider the, in general, this one is replaced with this one. So this is quantum mechanical operators. So, in summary, that is the total time derivative. What happens to the case of momentum operator with any mechanical variable? Any mechanical variable and momentum, conjugate momentum's Poisson bracket can be expressed in such a way: AP, AP, and QP, PQ summed over K, and subtraction. The answer is the operator, this mechanical variable A appears as a derivative of coordinate, and the momentum is momentum's partial derivative with respect to the momentum. And the remaining piece vanishes because momentum is taken the derivative by the coordinate. This one shows that mechanical variables derivative with respect to the generalized coordinate. So AP Poisson bracket is the Q's derivative for the mechanical variable A. Once the classical mechanics Poisson bracket is obtained, we can copy this result and replace this Poisson bracket with the quantum mechanical commutator, and then divide this one with IH bar is the derivative of the coordinate. Therefore, if I flip the order, we have negative sign on it, and the IH bar is multiplied to here. So commutator of P and A is minus IH bar, Q derivative of the mechanical variable A. Commutator is PA minus AP, and the remaining piece appears only if this operator acts on this mechanical variable A. So PA and the remaining piece cancel. PA is actually taking the derivative with respect to Q and multiply H bar over I. Therefore, in the configuration space in which the coordinates are fundamental variable, then the momentum is a derivative with respect to the coordinate, and the over factor is H bar over I. The correspondence principle can also be applied to the coordinate. Right before, we considered the Poisson bracket between any mechanical variable with the momentum, and now we consider the mechanical variable's Poisson bracket with the coordinate. Then by definition of the Poisson bracket, our value is AQ, and QP minus PQ. If we consider this, we have a Kronecker delta in the second term, and the first term does not have, it is vanishing because the coordinate is we take the derivative with respect to the momentum. Therefore, we have negative sign instead of positive sign. In the case of P, we have the first term survived, and in here we have next term, second term survived. So we have negative sign appears. This is originated from the Hamilton's equation of motion, in which the momentum time derivative has a negative sign on the Hamiltonian's coordinate derivative. Therefore, we just copy this one in here, exchanging Q and A. We have removed the negative sign on it. So Poisson bracket for the coordinate, generalized coordinate, and mechanical variable A is A's derivative with respect to the generalized momentum. Okay, so by applying the correspondence principle, we just copy this result and replace the Poisson bracket with the quantum mechanical commutator. Quantum mechanical commutator is given here, and the normalization factor was 1 over IH bar. Therefore, applying the same in a similar manner, we find that the operation of a coordinate operator Q on any mechanical variable is to multiply IH bar and take the partial derivative with respect to the canonical momentum conjugate to that coordinate. This is the momentum space representation for the coordinate operator expressed in terms of momentum's derivative. All right. Next, we consider the time evolution operation. In the configuration space, in quantum mechanics, we usually use Schrödinger picture. In the Schrödinger picture, wave function develops as time goes on, and the operators does not change at all as t goes on. It is opposite to the framework of the quantum mechanics and classical mechanics. In classical mechanics, we consider the particle's motion is position, velocity, acceleration, force, kinetic energy, potential energy, and so on, as a function of space and time. Therefore, the correspondence principle between the classical mechanics and quantum mechanics, as far as the time dependence is concerned, we have to consider the problem very carefully. That means Schrödinger picture is not an adequate picture to be compared with the classical mechanics. The picture that respects the classical mechanics structure is the Heisenberg picture. In the Heisenberg picture, the operator, for example, position, momentum, energy, and so on, depends on time. Instead, the state cat does not develop as t goes on. So let us, we might want to study the Heisenberg picture in the next step. Anyway, before we do that, we just consider the basic structure of a Schrödinger picture. In the Schrödinger picture, state cat develops as time goes on, and the state cat at time t can be obtained by multiplying the time evolution operator to the state cat at t equals 0. If we multiply this time evolution operator, then we have a wave function at time t. The position x of the state can be computed by taking the average value, and this average value is also called the expectation value, and that can be computed in the following way. We just insert the identity, that is the integral of the derivative product of the coordinate ket, and by using this we just find that this is a wave function at time t. So this one is a wave function at time t, and the position operator applied to the position ket, we read off the coordinate as y, and then this is sandwiched to the function to find that this is a psi star at time t at y. Because y is an integral variable, we can always replace with x. So expression in x is expressed like that. In this calculation, we use that this x on this position x, because x is a positive definite value, the eigenvalue for this x operator, for this x cat, x bra is x, and x star is x, the same. When we compute the linear momentum, we do the same job, and P is sandwiched by the state bra and cat, and we insert identity operator, that is the direct product of x and y integrated over x and y. We have two integrals over x and y, then y xx direct product appears. Alright, we do not need this, so just to leave this one p and combine this with integrate over y. And then this is a complex conjugate of a function at time t. Right side is the operator p appears. This operator p actually is equivalent to the derivative with respect to x of the wave function. That is this. So operator in the configuration space is a derivative of the coordinate of what this wave function. Okay, therefore this one is replaced with the wave function at time t. In a similar manner, we can also compute the total mechanical energy of the system. Total mechanical energy of the system, expectation value can be obtained in such a way. Hamiltonian is put here, and we insert identity matrix, identity operator, that is the derivative product of position bra and cat, integrate over the space. And now this is a complex conjugate of wave function at time t, and if we apply the Hamiltonian, then this value is just the kinetic energy and potential energy expressed in the configuration space, and this one is replaced with the wave function. Again, this Hamiltonian appears, any operator appears, then that operator in this is configuration space where x is used as the fundamental variable. This kinetic energy operator and potential energy operator x on the wave function. In the configuration space, this is a simple function, but the momentum should be replaced with the derivative operator with respect to the coordinate. And this part is the complex conjugate of the wave function. Next, we consider the state ket wave function in the momentum space. Quantum mechanics, in classical mechanics, the momentum conjugate, canonical conjugate momentum, conjugate to the coordinate, and the coordinate, they are equivalent. Actually, we can either use coordinate as a fundamental variable, or we can use the momentum as a fundamental variable. In either case, if Q is used as a fundamental variable, momentum should be replaced with the derivative. If you use the P as the fundamental variable, then you must replace the coordinate in terms of the derivative with respect to the momentum. Therefore, we can either use configuration space or momentum space. Usually in the bound state problem, like a hydrogen atom, it is better to use the coordinate space, that is a configuration space. However, if we consider a scattering problem, it is better to use the momentum space because the initial state and final states are prepared very well in terms of a momentum space as a single, very simple state. Therefore, it depends on the situation whether you make use of the momentum space or coordinate space. The momentum space wave function is expressed as this way. What we have done is just to replace the x cat with the p cat, that is a momentum eigenstate. Right. The position can be read off with the derivative of operator with respect to the momentum, and each component can be read off in such a way. Now, this del operator is not the derivative with respect to the coordinate. Instead, it is the derivative with respect to the momentum. If you read off the momentum of the particle, then because this state cat is eigencat of momentum, you just read off the number p vector outside. If you are interested in having the position, then you take the derivative. If you are interested in computing the total mechanical energy, then what you really need to do is to apply the operator in the momentum space to the momentum space wave function. The momentum space wave function is a function of p, and the kinetic energy must be expressed in terms of a simple number. Instead, the potential energy contains the coordinate x, and that coordinate x must be replaced with the derivative with respect to the momentum. Next, we consider the Schrödinger picture and Heisenberg picture. In the Schrödinger picture, operator does not evolve, and only the state cat evolves as t goes on. So, average value of a mechanical variable is evaluated in quantum mechanics as average value for sandwich, the operator sandwiched by the state cats and Brown. For simplicity, in this class, we do not consider the case that the mechanical variable A is free of explicit time dependence, and even the Hamiltonian does not have any explicit time dependence. Whether we use the Schrödinger picture or Heisenberg picture, the answer should be the same. And Heisenberg picture is a picture in which the state cat does not evolve, and only the operator evolves as t goes on. So, Schrödinger picture, time dependence appears only in the state cat, operator is time independent. We recall that state cat at time t can be obtained by multiplying the time evolution operator ut to the state cat at t equals 0. Then the Schrödinger picture expectation value should be of the form. Here state cat is at t equals 0 and the operator, this is operator, and this time evolution operator is attached to the operator. This is called the Heisenberg picture. In the Heisenberg picture, state cat is fixed to the value at t equals 0 and operator has the complete time evolution. Alright, so we put the subscript h to distinguish this approach from those in the Schrödinger picture. So in the Heisenberg picture, psi is fixed. This operator in the Heisenberg picture contains all time dependence. Alright. As a result, Heisenberg picture operator is expressed in this way, and Heisenberg picture state cat is expressed as an initial value in the Schrödinger picture. We recall that in classical mechanics, any mechanical variable has the Poisson bracket with the Hamiltonian with time derivative like that, if there is no explicit time dependence on that mechanical variable. In addition, if we apply the correspondence principle, then we have a quantum mechanical counterpart, that is a time derivative of the operator is 1 over IH bar, quantum mechanical commutator of that operator with Hamiltonian. Alright, the time dependence into quantum mechanics is allowed only if we introduce the Heisenberg picture. So Heisenberg picture operator should be used to make a correspondence principle. If we make use of the Schrödinger picture operator, this one does not work. Now, if we substitute the evolution operator, and this is the left hand side, this IH bar appears, this IH bar appears here, time derivative, because the time evolution operator has only the time dependence, we just have replaced the partial time derivative. Okay. Then the right side is the commutator with A and H, but this one should be written in the Heisenberg picture. So I have written the Heisenberg picture operator and Hamiltonian. So we introduce a trial solution. Because U is unitary, it should be of the form exponential I real parameter times Hermitian. That is a Hamiltonian. Okay, so we also have stated that we do not have any explicit time dependence in the Hamiltonian. Thus, if we substitute this one in here, we have I lambda here. Therefore, derivative gives minus h bar, lambda's time derivative Hamiltonian, and this. Its dagger has the same, except that we have negative sign, negative sign. Remember that because U is unitary, we have to choose lambda to be a real number. If we go ahead with the calculation, what we find is taking the time derivative, we have some commutator of the Hamiltonian and Schrödinger picture operator. But actually, this time evolution operator can be absorbed inside, and everything should be written in terms of the, and this is Hamiltonian commutes with this Hamiltonian. Therefore, this operator commutes to arrive at just in front of AS, and this one arrives at just in front of AS, just behind AS. Therefore, these are actually the Heisenberg picture operators. The commutator of the Heisenberg picture operator, AH, and the Hamiltonian is given here. An overall vector appears here, and right inside, the constraint coming from the correspondence principle between the classical mechanics and quantum mechanics gives AH8. Therefore, we have the differential equation that h bar time derivative of lambda is -1. That means this lambda is minus t over h bar plus some constant. And we throw away this constant because it contributes only to the constant phase and does not make us any physical result. Then the wave function in the configuration space at time t can be expressed as the x projection of the state ket at time t. The state ket at time t can be moved from the t equals 0. Because of what we find for the time evolution operator is this, we just substitute this time evolution operator in here. Therefore, the state evolves with this multiplication factor. If we remove this x, then what we find is the state ket evolves with this factor. This is a time evolution operator. Application of the time evolution operator has this kind of structure. Exponential. And if I take the partial time derivative, I have this overall factor. Then, if I apply IH bar at both sides, the right side overall factor disappears, remaining Hamiltonian only. And left hand side, it is IH bar time derivative, partial time derivative. If we apply this one to the state ket at time t equals 0, what we get is IH bar partial time derivative of the state ket at time t and the Hamiltonian state ket at time t. So, this is our final result for the time-dependent Schrödinger equation. Time-dependent Schrödinger equation states that the evolution of the state ket with respect to time is given in such a way. Alright, so in the position space, state ket at time t has this kind of form. Projection of x space will give, because there is no time dependence in the coordinate ket, we can pull out this derivative outside, and this is a function, wave function at time t. Right side, if we carry out the calculation in the configuration space, this Hamiltonian is replaced with our operator with kinetic energy and potential energy outside of wave function. And then, because P is an operator in the configuration space, we can replace this one minus h bar square over 2m del squared plus potential energy. This is the explicit form of the time-dependent Schrödinger equation in the configuration space. In summary, we have studied that the time-dependent state ket in the Schrödinger picture can be expressed as the product of the state ket at initial state ket at t equals 0. And this is called the time evolution operator when the Hamiltonian does not have any explicit time dependence. The time evolution operator satisfies this is U, satisfy this differential equation. And if we apply this method, this one, to the state ket at t equals 0, what we obtain is the time-dependent Schrödinger equation. Pulling out the wave function at time t can be made by projecting the state bra to the state cat. And translational, and we find the time evolution operator has the similar structure as the translational operator and rotational operator. Time evolution operator has the generator, which is the Hamiltonian of the system. Translational operator has the generator, which is the linear momentum operator. Rotational operation can be made with the exponentiated form with the real parameter and the orbital angular momentum operator as the generator of that operation. In quantum mechanics, there exists another angular momentum, intrinsic angular momentum, that is called spin angular momentum. Actually, this orbital angular momentum should be replaced with the total angular momentum, so that we can consider the orbital motion and the spin angular momentum contribution all together. That's it.